Hello there, and welcome back to Math 141 Recitation, Summer 2020. We have episode 9 in store for you today. Very exciting, as, 9 is a perfect square. And actually, we're coming right off the perfect cube of 8, so really on a hot streak here. Today, we are changing the differentiation game. Of course, where that chain is as in chain rule. That's going to be section 3.6, the chain rule. So where I finally get to use the chain rule legally. I am so very excited. I know that you're excited as well. And then we are also going to do some problems from section 3.7, implicit differentiation. So we're used to differentiating things that look like y equals some function of x. But here we start looking at differentiating functions which are not given to us so nicely. And we see that we can do that just as well. So not a ton of problems on this homework. So we're probably going to end up doing, about half or somewhere between a third and a half of them. So lots of good stuff in store for you today. And let's jump in with the very first problem, which is problem 4. We're going to go on a streak here at the beginning of like 4 or 5 straight homework problems. I think 5 of them, all the way from 4 through 8. So our first problem here asks us to write a function. So write the following function. In the form. So this is going to be setting us up for the chain rule. So it's going to be the form y equals f of u and u equals g of x. And then we're going to find the derivative dy dx, so the derivative of y with respect to x as a function of x. Okay, so we're going to first write y as a function of u, but then we're going to find the derivative of y as a function, oops, I shouldn't have ended the sentence, as a function of x. All right. The function which we are going to be working with in this first problem is y equals, big parentheses, x squared over 6 plus 5x minus 3 over x, all raised to the 6th power. So that's a doozy. We got fractions, squares, and then all of that stuff is raised to the 6th power. So this looks really scary at first, doesn't it? Oh my. So the first thing that we're going to want to do, in order to break this down and make it more manageable, is we're going to want to write y as a function of u, and then u as a function of x. Well, so in other words, what we're going to want to do is we're going to want to kind of break this thing up into the composition of 2 functions, which are easier to work with. So what we notice here is that, well, if I put all of this together, everything except for the 6th power, and let's just say I call this a, well then this gives me that y equals a to the 6th power. And that looks much more manageable because this is just a power rule situation if I was trying to take this derivative, right? And the derivative of x squared over 6 plus 5x minus 3 over x, it's kind of scary because of the fractions, but this is just going to be applications of the power rule. So we notice that, and because of that, what I'm going to do, I'm going to go ahead and erase these because I'm going to change the label. But we're just going to take that exact observation and use that to create our functions y equals f of u and u equals g of x. So if I let u, if I let u be this inside part here, so if I let u be x squared over 6 plus 5x minus 3 over x, well then y is just u to the 6th power, right? Because all of this stuff is u. All of this stuff in the parentheses is u. And y is just that stuff raised to the 6th power. So now let's check. I've written y as a function of u, right? So y equals f of u. Yep, y is written as a function of u. And I've written u as a function of x, right? u here changes based on x. Yeah. Okay, so we've got our two functions now. And so what we have, so we have y equals f of u. So y equals f of g of x, right? Where u, so this guy is equal to g of x up here, the u function, and y, we're calling this f of u, right? So what we get is that y equals f of g of x. In other words, plug in g of x into the function for y. So now we can go and take that derivative, and this is where the chain rule is going to come in. So dy dx, remember, so this is going to be the chain rule in general, so it's going to be f prime of g of x. So we're going to take the derivative of y and take the derivative of f and plug g of x into that derivative. And then we're going to multiply that by the derivative of g. And this rule here, this is the chain rule. Okay, so that's what we're going to do here. So let's first compute f prime and g prime. So let's do, so f prime of u, remember f is a function of u. F prime of u, well, f of u is u to the sixth. So that's going to be 6u to the fifth. This is just the power rule, right? So we're going to bring that 6 down front and then lower the exponent by 1. So f prime of u equals 6u to the fifth. And let's go ahead and compute g prime of x. Okay, so g prime of x is, okay, so g prime of x is, okay, so g of x is x squared over 6 plus 5x minus 3 over x. So actually first let me go ahead and rewrite just g of x to make this a little bit easier. So I'm going to rewrite it as 1/6 times x squared. And you don't have to do this, but I think this will make it a little bit easier. Plus 5x. And then rather than write it as 3 over x, I'm going to write that as 3 times x to the minus 1 power. Remember, 1 over x is just x to the minus 1 power. The great thing about writing it like that is that now I can very straightforwardly just apply the power rule to each of these 3 pieces. So if I first look at 1/6 x squared, bring that 2 down front, and I get 2/6 x to the first power now. This 5x, well, I'm going to bring the 1 down from the exponent, and I just have plus 5x to the 0 power. We'll go ahead and simplify that in just a second. And then let me see, I'm going to have minus 3 multiplied by negative 1, and then lower the exponent, so minus 3 times negative 1, x to the negative 2. Well, let's go ahead and simplify that as promised. This is just, so 2x over, well, 2/6, that's just 1/3, so that's x over 3 here. And then x to the 0 power, well, that's just 1, so this is just plus 5. And let's see, I got a minus and a plus here, or excuse me, 2 minuses, so that turns into a plus, that's what I meant to say. And then x to the negative 2, well, that's the same as dividing by x squared. Okay, so let's look at our formula again. So our formula says take f prime, okay, and then in f prime, for u, we're going to substitute in g of x. So I'm going to substitute this guy, g of x, in for u here. So we're going to get dy dx equals, okay, so that means it's going to be 6 times, now u to the fifth, so u is 1/6 x squared plus 5x minus 3x to the minus 1. And then that's u to the fifth power, so this should be to the fifth. All of that, oh man, I have to go to a second line, times now, we'll go back up here, times the derivative of g of x, so times g prime of x. And g prime of x we just computed, so that's times x over 3 plus 5 plus 3 over x squared. And that gives us a solution. It's not the most beautiful solution, but it certainly works. And that's the solution to this particular problem. I don't know about you. I oftentimes feel very proud and satisfied whenever I take a derivative and it turns into something really ugly. Because I'm like, yeah, I did that. Like, this thing looks wild, and I did that. I don't know. Anyways, so again, what we did here, you don't have to do this. For this problem, you do. But generally speaking, it can be a good idea to write your functions whenever you see that you're going to have to use the chain rule, to do this trick where you write y as a function of u and u as a function of x. Then you can just take all your ingredients and plug them into the chain rule here. So that's what we did. Down here, we computed all of our ingredients, our f prime and our g prime, and we plugged everything in. Okay, so like I said, in terms of writing the functions in that way that we did, that's going to be a very good thing whenever you get started with the chain rule. In time, you might feel comfortable kind of skipping that step, and that's okay. But for now, that's definitely a good way to get started. Problem 5 has similar instructions. So write the function in the form y equals f of u and u equals g of x. Then find dy dx, find dy dx as a function of u, or function of x, function of x. So the function here is y equals secant cubed of x. Okay, well this one actually looks fairly similar to the previous one. It does look different on the surface because we've got trig here. But notice, just like the previous one, I've got something, namely secant, raised to some power, right? In this case, 3. So it's actually going to work in a very similar way, where our y, we're going to write as, we're going to take this exponent here. So I'll write it in green, actually, so it corresponds. So then y is going to be u cubed. Okay, and this is going to be our f of u, remember? That's what we're calling it. Oh, should I write it in yellow? We'll see. So then u is g of x. Actually, I'll write the function first, and then I'll write equals g of x. So u then is the secant of x piece. Secant x equals g of x. Right? So we can see that if I were to write y, or f of g of x, then I would indeed get this function for y. Okay, so again, let's write down the chain rule just to remind ourselves. So the chain rule, so dy dx equals, so it's going to be f prime of g of x times g prime of x. Okay, so that's going to be the rule. Let's go ahead again and compute our ingredients here. So dy dx, or excuse me, f prime of u, okay, well, so f of u equals u cubed. So if I take the derivative of that, that's just a nice straightforward power rule. Bring that 3 down, lower the exponent, 3u squared. Now for the derivative of g of x, so g prime of x. Ooh, derivative of secant, that's a good one. That's one of those that I hate to say it, but you probably should just memorize. We could derive that just using the quotient rule, Remember, secant is 1 over cosine, so we could do that using the quotient rule. Or in fact, you can also derive that using the chain rule. But either way, as my analysis professor says, by hook or by crook, the derivative of secant is secant tangent. So now, whenever we go to plug that into our chain rule, dy dx, okay, well, dy dx equals f prime, so that's 3u squared, but that's 3u squared, but u is going to be g of x, right? That's what this is getting at here, where we have f prime of g of x. Well, u was secant, so this becomes 3 secant squared x, right? We're just plugging in u equals secant of x. And then we're going to multiply that by g prime of x, and g prime is right there as secant times tangent. Okay, and we can combine our secants there and write that as 3 secant cubed x times tangent of x. And there we go. We've got our derivative, dy dx, as a function of x. Yay, ta-da! So fun, good old trigonometry. Who doesn't love it? You don't have to answer that. Okay, let's now move on to problem 6. Problem 6 is kind of going to get at what I was saying a moment ago, where it doesn't ask us this time to break it down into the functions f and g. So we're kind of going to skip a little bit of a step now that we're getting a bit more comfortable with chain rule. Again, if you would like to, we certainly can, and maybe we'll see how it goes. Find the derivative of the following function. Okay, so my function is y equals 1/12 times 4x minus 5 cubed plus 5 minus 1 over 3x cubed, all of that to the minus 2 power. Okay, so this looks like a bit of a doozy. Kind of got a lot going on. But we're really just looking at 2 pieces, right? We can just differentiate this first piece and then differentiate this second piece, since they're just being added, not multiplied. So that makes things nice. If these are being multiplied, oh my goodness, we would be in for a long night. But thankfully, they're just being added. So let's go ahead and look at this first part. So let's first focus on the 1/12 4x minus 5 cubed. Okay, well, what I'm going to do, so I'm going to treat 4x minus 5. So let me write this part real quick. So 1/12 4x minus 5 cubed. Well, I'm going to treat, I won't go through all the details like we did in the first 2 problems, but I'm going to treat this as just u. Okay, 4x minus 5, I'm just going to call that u. So then, when I take the derivative, so derivative, well, if this was 1/12 u cubed, all I would do is I would bring that 3 down front, right? So let's go ahead. In fact, let me go ahead. And we can write this as 1/12 u cubed, where u equals 4x minus 5. So if I take this derivative now, I'm going to bring the 3 out front, right? So I'll get 3/12 u squared. Well, u is 4x minus 5 squared, right? So remember this thing, 4x minus 5. This is just u. And now I need to multiply by the derivative of u because of chain rule. Well, the derivative of u, well, u equals 4x minus 5. And the derivative of 4x minus 5, well, the derivative of 4x, that's just 4, so times 4. And the derivative of 5 is 0, so it's just times 4. Okay, so this part over here, this is our u prime. Okay, so let me rewrite this and we can simplify a little bit. So this gives me, well, 3 over 12, that's just 1 over 4. And then I've got 4x minus 5 squared. And then 4 minus 0, a normal person writes that as 4. And now look, I've got 1/4 and times 4, so this is really just 4x minus 5, quantity squared. Okay, so that gives us our first part. So I'll put a star here. I don't want to put a box around it because it's not our final answer. We'll put a star there. So that gave us the derivative of our 1/12, 4x minus 5 cubed. So let's move on to the second part. 5 minus 1 over 3x cubed. Now let's change over to red. Excuse me, so let's do 5 minus 1 over 3x cubed. All of this raised to the negative second power. Okay, so I'm going to do a little trick, which I've done before. I am going to rewrite the 1, well, first of all, let me rewrite this as 1 over 3 times 1 over x cubed. So negative 2, right? You'll agree with me there. If you multiply the 1/3 times 1 over x cubed, you will get 1 over 3x cubed. And now, times 1/3, well, 1 over x cubed, this is just x to the minus 3. So I'm going to write that here. 5 minus 1/3 x to the minus 3, and then all of that raised to the minus second power. So now what I'm going to do, I'll call it a different variable this time just so we don't get confused. So I'm going to call this thing v, okay, this 5 minus 1/3 x to the minus 3. So this thing is really just v to the minus second power. Okay, so now I'm going to take the derivative of that. Take derivative. Okay, well, I'm going to bring that minus 2 out front. And then I'm going to have a v here. Well, v is 5 minus 1/3 x to the minus 3. And now I'm going to lower that minus 2 by 1. So that's now a minus 3. And now I need to multiply by the derivative of v. Okay, so now times, what I'm going to write here is going to be, so this is going to be, remember this part here is v. And over here, what I'm going to write in just a second is going to be v prime. Well, let's take the derivative of 5 minus 1/3 x to the minus 3. The derivative of 5 is 0, so that just goes away. And then the derivative of the minus 1/3 x to the negative 3. Again, that's just a power rule. So multiply by the negative 3, bring the negative 3 down. And that's going to turn that negative 1/3 into a positive 1. So I guess I'll go ahead and write it here just to be clear. Let me go on to another line, actually. Times, so we're going to write v prime down here. This will be v prime. Okay, so I will have the derivative of 5 is 0. And then I have minus 1/3 times a negative 3 from the exponent of the x. And then I'm going to lower that exponent for x by 1 to negative 4. Sorry, this is kind of messy. It's these two things multiplied together here. And so this will give me negative 2 times 5 minus 1/3 x to the minus 3 all to the negative third power. And now let's see, what does this simplify to, our v prime? Well, the negative 1/3 and the negative 3, those multiply together to just make a 1. So I'm actually just going to ignore them. And the 0, well, the 0 doesn't do anything. So this is just times x to the negative 4th. Times x to the minus 4. If you want, you can instead write, over x to the 4th. That is perfectly fine. But this gives us the derivative which we seek. Oh, excuse me, no it does not. Because this was just part of the bigger problem. Excuse me. That was silly of me. Okay. So now we've got let's star this thing. And now let's go and put everything together. So now dy dx is equal to, okay, our first part was 4x minus 5 squared. And now we add in the second part, so minus 2, 5 minus 1/3 x to the minus 3, all raised to the minus 3 times x to the minus 4. And this is our final answer. We have to put everything together. Totally forgot about that. Okay. Alrighty then. Let us move on to the next problem. Which problem was this? This was problem 6, okay. So next I would like to do problem 7. Problem 7, more chain rule. Gosh, I love chain rule. Find the derivative of the function so the function is y equals 2x e to the minus 3x minus 2 e to the x cubed. Okay, hydrate or dihydrate. And I will choose the former. Because if I dihydrate, then I can't do any more math. And that means I can't do any more chain rule. Okay. So, again, we've got kind of two pieces here, so we can differentiate each of them in turn. So let's first focus on 2x e to the minus 3x. Okay, well here, I noticed that I've got a product of two functions. So let's call 2x, so let's write this as f of x equals 2x and g of x equals e to the minus 3x. So now we're going to have to apply the product rule because I've got two functions being multiplied together. Yay, product rule. So you'll remember that that says that the derivative of f times g is the derivative of f times g plus f times the derivative of g. I think last time I wrote it slightly differently. It doesn't matter, right? So long as you have the derivative of f being multiplied by g plus f times the derivative of g, you can switch up the order. It makes no difference in this case. So let's go ahead and compute this. So let's go ahead and compute our ingredients first. So f prime of x is going to just be 2. That's a pretty nice power rule. Now g prime of x is going to be a bit trickier because now g prime of x is going to involve chain rule, right? Because I've got e to the, and then I've got this other function sitting up here, this negative 3x. So if I let negative 3x equal u, well then what I'm going to do is I'm going to take the derivative of e, okay? So actually let me go ahead and do this one in a bit more detail because this is an important example. So before we write what g prime of x equals, what I'm going to do is let me see. So I'm going to let f of u, we're going to do this like we did the first couple. Let f of u equal e to the x, or f of equal e to the u. Yeah, let f of u equal e to the u. And u of x equal, so in this case, our function in the exponent is negative 3x. Okay. Oh, let me change the name of this first function. We already defined an f. So let me call this function, I don't know, let's call it h. Okay, so the derivative then, so notice that, yeah, so then the derivative of h of u of x, so h of u of x, well, that is equal to e to the minus 3x. So this is just g of x, right? That's g of x, as you'll recall from up here. Which means that the derivative, using chain rule, is going to be h prime of u of x times u prime of x. Okay, well, h prime of u, well, it's just e to the u, and the nice thing about e, you'll remember, is that it is its own derivative, so h prime of u is just e to the u, and g prime of x, or excuse me, u prime of x, well, that is just negative 3, because it's just negative 3 times x, so that's just negative 3. So what we can see then is that g prime x, so g prime of x, equals h prime, so that's e, and then for u, so h prime of u of x, well, u of x is negative 3x, so e to the negative 3x, times the derivative of u, which is negative 3, so times negative 3, or in other words, negative 3 e to the minus 3x. Okay. So now I have my f prime, and I have my g prime. So now I'm ready to apply the product rule. So the product rule says first I want to do f prime, so that's just a 2. Okay, so now, what color was I using up here? Okay, so I have, so 2 times, now I'm going to multiply that by g of x. So g of x was e to the negative 3x. So 2e to the negative 3x plus, and let me see, so plus now f times g prime. Well, f is 2x, so plus 2x, and then g prime, we just computed, was negative 3 e to the negative 3x. And so this we can simplify to 2e to the negative 3x, and then it looks like minus 6x e to the minus 3x. Okay, so this is our first derivative. Remember, we have these two pieces again of this function. So we just took the derivative of this first part, 2x e to the negative 3x. And now we have to take the derivative of 2e to the x cubed. So let's go ahead and write that. So now I have 2e to the x cubed. All right, well, again, it looks like I'm going to have to chain here. And so if I let this x cubed, so let x cubed equal, oh, I don't know. If I just call this, we'll call it v. Well, then whenever I take the derivative, well, then this just becomes 2e to the v. So now I take derivative, and I have 2 e to the v, so v is x cubed, but I need to multiply that by the derivative of v, by v prime, because of chain rule, and v prime is just 3x squared, so then 3x squared equals v prime, so times 3x squared. So this is v prime here. And that gives us the second part of our derivative. So our total derivative, whenever we put everything together, we get dy dx equals, all right, I have 2e, so negative 3x, minus 6x, e to the negative 3x, plus, let me go ahead and I can combine some stuff up there. Let me see, it looks like I'm going to get a 6x squared times e to the x cubed. So it looks like this is my derivative. All right. So we're getting more and more comfortable with chain rule. Here, we got to see chain rule within product rule. So that was wild, but we were able to make that work. Okay. Really, as long as you're careful and you break everything down and you take your time with it, you should be in good shape. Okay. A lot of this stuff looks really scary right away, but then whenever you start to break it down, you say, okay, this is doable. I can do this. The next problem, which I would like to go over, is going to be problem 12. I think I was going to do 8, but as I look at the clock, I think that it would be in the best interest of time to jump to problem 12 and start some implicit differentiation. So again, we're used to differentiating things that look like y equals some function of x. But now we're getting functions which are defined a little bit more differently, a little bit less, more differently. It sounds wrong. It sounds weird, but I think it's right. I don't think there's anything grammatically incorrect there. Use implicit differentiation, there we go, to find dy dx. And the function is x equals cosecant of y. So it kind of looks like something we've done before, right? Except instead of y equals some function of x, we have x equals some function of y. So the way that I think about implicit differentiation, this is another topic which I think looks really hard and weird, but the way that I think about it helps me break it down into stuff which I'm used to doing. So we're going to take the derivatives of both x and y, derivatives of both x and y, and everywhere that we see, and every time we take a derivative of y, we take derivative of a y term, I'll call it, derivative of a y term, you write dy dx next to it. Right, dy dx next to it. And then you can just solve algebraically for dy dx. Solve algebraically for dy dx. So we'll of course go through a couple examples, but this is kind of going to be the idea. We're just going to take the derivatives like we always have, and we're just going to make this slight modification and then do a little bit of algebra with it. So let's see how it plays out here. Let me copy down the function again because I took up so much space. So we have x equals cosecant of y. Okay, well now let's go ahead and take the derivative. Well, when I take the derivative, the left-hand side, the derivative of x, you and I know that's just uno, 1. I almost minored in Spanish in college. So that's just 1, and then on the right, so that's cosecant of y. Well, the derivative of cosecant, ooh, I know you remember this one. If not, you should. It's a tricky one, I know. Excuse me, not cosecant of x, it's going to be cosecant of y times cotangent of y. And now, because we are taking the derivative of a y term, we're going to write dy dx next to it. We're going to multiply by dy dx. Okay? And now all that you have to do is just solve for dy dx. And to do that, we just divide both sides by negative cosecant times cotangent. So that's going to give us negative 1 over cosecant y cotangent y equals dy dx. And depending upon how fancy we are feeling, let me see. Well, cosecant, this is just 1 over sine of y. And cotangent, well, I'm just 1 over tangent of y. And so really, let me see, this just comes out to, so this is negative, since it's 1 over sine, that just becomes negative sine of y times tangent of y equals dy dx. So notice here that the derivative doesn't actually depend upon our value of x. The derivative here is going to be entirely determined by the value of y, which is unusual. We're used to, again, whenever we've taken these calculations before, the derivative of the function has only depended upon x. Remember, the derivative is the slope. But here, the derivative actually doesn't depend upon x at all, right? There's no x's in our formula here. It only depends upon y. So this is one advantage of implicit differentiation, is it lets us do that. Okay. The next problem, which I would like to do, is 14. I'm going to skip over 13. 13 is quite similar to 12, I think. So let's jump to 14. And this says find dy dx. And we have e to the 9x equals sine of x plus 4y. Now notice that the problem doesn't come out and say explicitly use implicit differentiation. The way that we know to use implicit differentiation is that we can't write this in the form y equals some function of x. I mean, we could if we really, really wanted to. Like, we could take arc sine of both sides. Like, we could do some algebra to make it work, but it would make things a whole lot more ugly. And so, for all practical purposes, we can't really do that. Again, technically can we? Sure. But it's going to make taking the derivative a real pain in the butt. So this is how we know to use implicit differentiation. This is the key. With that said, let's go ahead and do it. So again, we're going to take the derivative of both sides. So we get to take the derivative of e to the 9x. Okay, well, let's look at how we do that first. Derivative of e to the 9x. And here, I would like to actually do something a bit more general. So let's find, so for any function f of x, let's find the derivative of e to the f of x. Okay, so here, in this case, we have f of x equals 9x. But we've been doing a few problems now. When we go back up here, we were taking derivatives of e to the x, where we had e to some function of x. And it was kind of a lot of work whenever we did it there. So it'd be great if we can find a nice general way of doing it. Well, here's what I'm going to do. Well, okay. How do I want to write this? So so y equals e to the f of x. Okay, so I'm going to write y equals e to the u, okay, where u equals f of x. This is, again, kind of going back to what we did at the beginning of this video. Okay, so y equals e to the u, where u equals f of x. So dy dx is going to be the derivative of e to the u. Well, that is just e to the u, but we're going to plug in f of x times, and now we have to multiply by the derivative of u times f prime of x. And so this gives us a nice general way of doing it. I should have circled the dy dx as well. And you might say, well, that doesn't look much simpler, but let's look at our specific function. This tells us that the derivative of e to the 9x, well, 9x, remember, is just f of x in this case. So if we use our rule above, then this just becomes e to the 9x, right? Again, just plug in 9x here. F of x is 9x. And the derivative of 9x is just 9. So that's 9. So 9e to the 9x. Okay, so that gives us the derivative of e to the 9x. I realize that might seem like a lot of work, what we just did. But if you take this rule and get familiar and comfortable with it, this can save you a lot of time in the future. If you want to take the derivative of e to some function of x, you leave the e part alone, and you just multiply it by the derivative of your exponent. Okay, so now going back to the problem, we have 9e to the 9x equals, okay, and now we want to differentiate the right-hand side. Okay, well, this is going to be a chain rule because inside of sine, I've got x plus 4y. Right, so if I let x plus 4y, let's just make this another function. Let's just call this thing a. I don't know what to call it. Okay. Well, then let me see. So if I take the derivative of that, that's going to be cosine of a times the derivative of a because of chain rule. So cosine of, oops, I don't want that to be in black. I do want it to be in black. That's cosine of a. A in this case is x plus 4y. So cosine of 4x plus y, x plus 4y, x plus 4y. Now I need to multiply by the derivative of x plus 4y. Okay. Well, the derivative of x plus 4y, so this, let me just write, this was our a, if that was helpful for you. This thing will be a prime. The derivative of x is just 1. And the derivative of 4y is just 4. But remember, since we're doing implicit differentiation, we're going to stick a dy dx there. Because anytime we take the derivative of y, we stick a dy dx. And now we just solve for dy dx. So 9e to the 9x equals cosine of x plus 4y. And then if I multiply, so then I have to distribute, so plus 4 cosine of x plus 4y dy dx. Okay, so let me see. Let me subtract cosine x plus 4y from both sides, and I get 9e to the 9x minus cosine of x plus 4y. equals 4 cosine x plus 4y dy dx. So then I divide both sides by 4 cosine x plus 4y, and I get 9e to the 9x over 4 cosine x plus 4y minus, well, now whenever I divide this cosine x plus 4y by the other cosine x plus 4y, those are going to cancel, and I'm really just dividing. Basically, I'm just going to end up with the 1/4 here. Again, because the cosines, those parts will cancel whenever I divide both sides of this by that, equals dy dx. And maybe we could split this up a little bit. I don't know. But this is certainly one way to express our answer. Okay. So again, in this case, we developed a very nice rule for differentiating e to some function of x. You're always going to leave the e to the x part alone, right? So in this case, we had e to the 9x, so we leave the e to the 9x alone here. And then we just multiply that by the derivative of our exponent. Okay? That's a very nice trick, something which you should get comfortable with. And then for the second part, we had to, again, use the chain rule, and we also had to do a little bit of implicit differentiation here. Okay, there we go. Let's knock out one more tonight, and then I am going to hit the hay. Let's finish up with problem 18. If I'm able to sleep, I'm going to be so jacked up after doing so much chain rule. I don't know how I expect to be able to sleep. Yes, okay. This one is a cutie. The point, the given, blah, 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 blah. The given point is on the curve. It's going to give us a curve and a point that's on the curve. Find the lines that are, so first we're going to find what we've always been finding. We're going to find the tangent. And then we're also going to find a new kind of line called the normal line to the curve at the given point. Curve at the given point. All right. So our curve, brace yourself, is 2x squared plus 9xy plus 8y squared plus 16y minus 2 equals 0, and our point is minus 1, 0. Holy smokes, okay. Well, we need to find the tangent line and the normal line. And to find both of those lines, really, to find the lines, we're going to need to find the right slopes. We need to find the slope of the curve at the point of the curve at minus 1, 0. And that means we have to find dy dx. Right? Because whenever we say if we're finding the slope of the curve, really what we're saying is we need to find dy dx. Exclamation point, because we're so excited to do that. Now notice in this problem, we're not given something nice in the form y equals some function of x. Sometimes you're given something that you can easily solve to put into that form, but I don't really see that here. And so our best bet is going to just be to do some implicit differentiation. Now again, this is going to look scary because look at how big this function is, this curve. But really, we're just going to be applying the power rule over and over again. So the derivative of 2x squared, well, that's just going to be 4x plus, okay, now we have to be careful. Let me see, so 9xy, so that's going to be 9x, and whenever we take the derivative of y, remember, we need to do a dy dx, plus 16y, now times a dy dx, again, because we're taking a derivative of y in this case, plus 16 dy dx, as always. The minus 2 goes away whenever we take the derivative. And then when we take the derivative of the right-hand side, we still get 0. Okay, so this isn't so bad. So what we're going to do is we're going to move the 4x to the other side. So 9x dy dx plus 16y dy dx plus 16 dy dx equals minus 4x. Now everything on the left-hand side has a dy dx, so we can factor that out. 9x plus 16y plus 16 equals minus 4x. And finally, to isolate dy dx, we divide both sides by the other stuff. So equals negative 4x over 9x plus 16y plus 16. Okay, so this is our derivative. Very nice. We are looking for, first, let's find the tangent. So we need to find the tangent line at the point negative 1, 0. So plug in negative 1, 0. Again, notice, so before, whenever we've done things, like whenever we found the tangent lines, we only plugged in a value of x. But now we plug in a value of x and a value of y because our derivative depends on both x and y. So if I plug in negative 1, 0, then I get that dy dx is going to be, okay, so negative 4 times negative 1 over 9 times negative 1 plus 16 times 0 plus 16. Let me see, that just on top just becomes a 4. On bottom, I get negative 9 plus 16, and that becomes 4 over 7. Okay. So now I have a point, negative 1, 0. I have a slope, 4, 7, which means that the tangent line is going to be, okay, let me do my point slope form. It's going to be y minus 0 equals m, so that's 4 over 7, x minus 1. Let me see, so in other words, this is y equals 4/7 x plus 4/7. And yeah, there we go. So that's our tangent line. I'm mostly going to leave the normal line to you, but I am going to tell you this part, which is the key. Other than this, it's going to just be like finding a tangent line. So remember, so if the tangent line has slope m, the slope of the normal line is negative 1 over n. Is negative 1 over m. Okay. So let's go ahead and figure out the slope of this, and then I will leave the rest to you. So in this case, the slope of the normal line, the reason for this, by the way, is just that the normal line is perpendicular to the tangent. Normal line is perpendicular to the tangent. And at some point along the line, I don't know if it was geometry or like algebra 2 or something like that, at some point along the line, we learned that if I want to find the slope of the normal line, we flip it and we put a negative sign. So the slope of the normal line in this case, normal line is, well, the slope of our tangent line is 4/7, so I'm going to flip it 7/4 and tack a negative sign on it. So now again, I still have a point because it's going to go through, it still goes through the same point, so it's going to again go through -1, 0. And now we have a slope. Okay? All right, so that does it for this video. I hope that you found it helpful. As always, please tell me how I can be as helpful as possible.